Yeah, that's not showing. All right, I am going to hold a special office hour today at 2 since I haven't held any yet. And we've got a long weekend and homework coming up. These calendar announcements should be propagating through Slack, so that's one thing that you should be checking Slack for is updates to office hours, updates, due dates will be announced on there as they approach, things like that. It's one good way of keeping on top of the course calendar. And then both Professor Jarbo and I are holding special office hours on Tuesday. So mine will be at 11 in my office, and Professor Jarbo's will be in the BRL atrium at 1 p.m. And again, you can always check Slack for those kinds of announcements. All right, there is the equation sheet for today going around. I won't always print them out for you, but I'll try to if I have the extra time in the morning to get that done. Any questions before we start today? No? All right, so we spent most of our time on Wednesday walking through the first law, translating it into an equation that we could start to calculate state changes with. And so we started working with a simple state change for an ideal gas confined to a cylinder that's being compressed. And there are a lot of different ways to go from the initial state, which is a larger volume, so this is 2.4 liters in this example, and then we compress it by a factor of 4 down to about 0.61 liters. And we do so in such a way that the initial temperature and the final temperature are the same. And we're starting to trace this first path that we can take to get from the initial state to the final state. So we calculated the first leg of this path. So that was isobaric cooling. That means constant pressure. And physically what that means, we take our cylinder and we put it into a really cold liquid to cool that gas down. And we let that piston settle as the gas compresses. And this, of course, is at elevated pressure. So maybe there's a weight on the piston to keep the pressure at 10 atmospheres. Okay, and so we were treating this as an ideal gas. So we were able to get the associated temperature change pretty easily. So we're compressing by a factor of 4. And what you'll notice is that the absolute temperature decreased by a factor of 4 as well, right? As a consequence of ideal gas law behavior. You have one of the independent variables, one of the other ones it's going to have as well. You've got a total of 3 variables that define the system, right? You've got pressure, volume, and temperature. You can choose any 2 of those to be your independent variables. And then the third one has to be calculated as a function of the other 2. So that's the degrees of freedom of the system is what we're getting there. And so there's a phase rule that we talk about, right? So 2 minus the number of phases plus the number of species, right? Okay, so working with the first law, we got the amount of work and the amount of heat that was required to do that cooling step. So there was compressive work done on the system because it got squished. And because we were cooling it, to do that squishing, there was heat that came out of the system as well. And tallying all those things up, we came up with about 6 kilojoules of heat that came out and about 1.85 kilojoules of work that went in. All right, so now what we'd like to do is come back So I've got the work and the heat summarized here. The overall change in internal energy then was about 4.3 kilojoules, negative 4.3 kilojoules. And now we are going to calculate the state change from step 2 to step 4. So this step is isochoric. That means constant volume. That means physically what we do is we jam the cylinder in place so it can't move. And now we're going to put this, we're going to take the cylinder out of its cold water bath, or it's pretty darn cold, so maybe it's a liquid nitrogen bath. We're going to take it out, we're going to put it back on the countertop, we're going to let it heat back up to 298, so right around room temperature. Piston isn't moving, so how much work is being done by or on the system? 0, awesome. That one's pretty easy. So equation-wise, remember that work is PdV minus PdV. So if dV is 0, that's what the isochoric means. You get to cross anything that has dV in it out, or any derivative of volume out. And then what you're left with is du equals dq. What does du equal for an ideal gas? It's on a couple of your equation sheets. And this should be one of the substitutions that you can make pretty quickly as we go through the course. If I wanted to calculate a change in U versus pressure for an ideal gas, how much change is there going to be from 1 bar to 10 bar if I keep everything else constant? Remember, for an ideal gas, U and H are temperature dependent only, right? And for an ideal gas, this pen's a little thick. For an ideal gas, the differential change in the internal energy for an isochoric process is just going to be the heat that's done, and also the identity for the differential change in du. Is that big enough to see? Sorry, dV. It's the constant volume heat capacity times the differential change in temperature. So if I want to know the heat, then what I'm going to do is I'm going to integrate dq on the left side, and I'm going to integrate cv dt on the right side. So let's go down to the bottom here. I do need a thicker pen. So Q24, dQ24 equals the ideal gas heat capacity of our working fluid, which was methane. So CH4 times dt. So Q24 is just going to be the integral from our low temperature, and our low temperature is 74.3. And our high temperature is 298 K. And there's going to be the dt and the integral, and now the heat capacity part, that's the part that we're going to look up in the back of the book again. So that is going to be A plus BT plus CT squared plus D T to the minus 2. And those are the coefficients that we look in the back of the book. At this point, we've got an integral to evaluate. And we can either remember what the closed formula is, we can rederive the closed formula, and that's going to be one of the most convenient things to do. So if you're doing these calculations with your graphing calculator, teach your graphing calculator that equation and just use it. Your calculators are programmable. So these are so error-prone, typing in that many numbers in your calculator. I don't know, even if you're really accurate with the keying, you're just going to have mistakes that are going to be frustrating you. The way that I like to do these is honestly either in a spreadsheet or in MATLAB. And I think since you all are learning MATLAB semester, I want to demonstrate how easy that is to do. So for Q24, we're going to do this one in MATLAB. So I'm going to go to the textbook. I'm going to go back here to the heat capacity tables. I am going to copy A, B, and C right out of the table. And so this time I want to get those into the notes. Okay, so those are written down now, and they're in the computer's memory. So I'm going to go over to MATLAB. My computer will let me do that. Here we go. All right, so I'm going to paste those numbers in. There we go. All right, so A equals 1.7. It's hard to see, isn't it? Now better? A equals 1.702. B equals 9.081. All right, now at this point I want to address the table notation. So up here at the top, it says 10 to the third times B. So what that means is the numbers in the table have been multiplied by 1,000 because they're all really small. You can make a great argument for why it means the other way. It doesn't. It means that the numbers need to be divided by 1,000. So we're going to put an E minus, sorry, we're going to put an E minus 3 in front of there. And then when I copied and pasted from the PDF, the negative sign didn't translate over correctly, which is why it's hard to see on the screen, but showing it in red. So I'm going to delete that and replace it with an actual minus sign. And then C equals minus 2.164. And if you go back to the table, that one's multiplied by 1,000,000. So I'm going to divide it by 1,000,000 by adding e to the e minus 6 out in front of there. All right, so now the numbers are in there, so I don't have to type them over and over again anymore. And so if I've made the mistake, it's up here and it's easy to see and it's easy to correct. All right, and so now I am going to put an equation into MATLAB for the heat capacity. If you haven't seen this notation before, the @ symbol followed by parentheses is called a function handle in MATLAB. And so that is a quick way to make functions to evaluate. So I'm teaching MATLAB an expression that I'm going to use over and over and over again. All right, and to be completely accurate, this polynomial that I'm entering in here for heat capacity is heat capacity of the constant pressure heat capacity, and then it's divided by R. All right, so the constant pressure heat capacity is A plus B times T plus C times T squared. So dot star, that's multiplication in MATLAB, and dot hat, that's exponentiation, so raising the power in MATLAB. And so that's the equation. And okay, so does anybody read in the book what the difference between CV and CP is for an ideal gas? As far as computing it. Yeah, that's right. It's the other way around though. So CV is always smaller than CP by a factor of R. Okay, so if this expression is CP divided by R, then how do I take off that factor? I'm going to subtract R over R from it, right? So minus 1. That make sense? So if CP is CV plus R, CP over R is CV over R plus 1. So CV over R is CP over R minus 1. Okay, so there is my equation, and it echoes back to me that I made a function handle with that value. So let me show you what it does. So CV over R evaluated at 298 gives me a number. If I add 1 to that number, that should be CP over R, right? Now, if I go back to my table, one of the things that it helpfully tabulates for me is what's the value of CP over R at 298 degrees Kelvin. So for methane, it says 4.217. That's this number right here. So now back into MATLAB, and look at that, it's 4.216 is what I got out there. Maybe if I put in the 0.15 into my Kelvin, it comes out to be the number they put in there. So that's that. So now I've got a function that I can use. And what am I going to do with that function? What I want to do is I want to calculate this heat capacity integral. So I'm going to tell MATLAB that I want to give me Q24, and I want it to integrate from 74.3 to 298.15 Kelvin. My CVIG over R function, and I'm going to choose my favorite value of R to multiply that by to get my final result. So my Q24 is going to be, say, 8.314. All right, now here comes the fun part. Rather than do any more typing or calculus, I'm going to type integral, and then in parentheses, I'm going to give MATLAB the name of the function that I defined. I'm going to give it the lower integration limit, and I'm going to give it the upper integration limit. Pardon? It's a long story, but sometimes you need the dot and sometimes you don't. And if you don't know, then just use the dot. Slightly longer story is the star is for matrix multiplication, which is going to get you different results when you multiply together arrays. So lists of numbers. If you're not worrying about matrix multiplication, then the dot version is always the one that you want to use. All right, so that comes out to be 4.297 kilojoules. So this result here is in joules. And so we'll put that back. Over here. So 4.297 kilojoules. And so my delta U for this step is equal to Q is equal to 4.297 kilojoules. All right, so when I promised when we started this is that since the initial temperature and the final temperature are the same, the overall change in internal energy needed to be 0. And let's double check that. So my calculation for step 1 to 2 gave me an internal energy change of negative 4.3 kilojoules. And then when I heated back up, I got back right around 4.3 kilojoules required. So to 2 sig figs anyways, I'm going to come out to 0. And if I included the extra digits in all the numbers, then it would have come out to be rigorously 0. All right, so to within numerical rounding, I'm at 0. All right, so now let's look at let's go up this time, and then we'll go to the left. So going up, so this is going to be another isochoric heating. And then, except this time, I'm going to be starting at 298 Kelvin. And I'm going to be ending at a T3. All right, so let me come up with a quick way of telling me what T3 is going to be. So in the first step, I cooled from 298 to 74.3, which is 4 times less than 298. Why was it 4 times less? Well, because the ultimate pressure is going to be 4 times higher, and so I need 4 times less volume. And I'm going in this direction. My purpose of the heating is to first raise the pressure, and then I'll reduce the volume. So if I want to quadruple the pressure of an ideal gas, what do I need to do to the temperature? I need to quadruple it. So my T3 is just going to be 298 times 4, which is 1192 Kelvin. Follow that? If that's too fast, you can just start writing down ideal gas law. So I know that P3 is equal to 40 atmospheres. And so I know that T3 is going to be P3 times V3 over R. You can work that calculation out on your own. I guarantee you it's going to come out to 1192 Kelvin. And V3, of course, was our initial volume of 2.44 liters. All right, so so what's the work in this part? 0. What am I going to do for the heat? I'm going to integrate that heat capacity equation with respect to temperature again. And I'm going to use 298 as my lower integration limit and 1192 as my upper integration limit. Nothing's changed as far as setup over here. So I can just go straight back to the MATLAB window here. And so I can say Q from 0.1 to 0.3 is going to be gas constant. And now we're going to integrate. This time we're going to start at 298. And we're going to go up to 1192. And so that is about 4.55, or sorry, that's times 10 to the 4. So that's about 45.5 kilojoules. So is that surprising at all that it's that much bigger? The numbers were a lot smaller in the first path. I mean, the temperature span that I'm covering now is much larger, right? So it's actually more than 3 times the temperature span. Last time I was just cooling by about 200 Kelvin, and this time I'm heating by about 900 Kelvin to get up to the final temperature. And so this is the reflection of that. So that's 45.5 kilojoules. And the work was 0. And the delta U is equal to the Q, again, for that step in the process. All right, and so now we are at the final pressure. So our isobaric cooling step now, that's going to be work equals minus 40 atmospheres times the change in volume. So that is going to be our starting volume, 2.44 liters, minus 0.61 liters. We're starting, yeah, you're right. Well, it should come out to be, no, it should come out to be negative because we are compressing. No, you're right. You're right. 0.61 liters minus 2.44 liters. So that, again, is going to be minus 40 times 0.61 minus 2.44. And that unit is the liter atmosphere unit again, right? Sorry, I forgot it already. 73.2. So that's 73.2 liter atmospheres. And there's a couple of different ways that I can think about converting that unit readily. I can do it directly. So if I get to what I want to get to is SI units, right? So if I transform liters into cubic meters, that's a factor of 1,000 downwards, right? So that's 1 to the minus 3 cubic meters per liter. And then the SI unit for pressure is Pascal, and It's 101,325 pascals per cubic meter. So 73.2 times 0.001 times 101,325, and that gives me 7,400 joules. The exact number is 7417. All right, now the Q for this part. Do you remember from last time how we calculate the Q for an isobaric cooling step? It ended up being equal to the change in enthalpy, right? And then change in enthalpy that again is a heat capacity integral, except this time it uses the CP version instead of the CV version. So now again, we're back to either punching it out in your calculator or using software to do it. All right, so at this point, I can go back to where I define my heat capacity equation in the software, and I can just omit that -1, and now I've got an equation that I'm going to enter for the constant pressure heat capacity. And to calculate the Q, this time we're going to integrate CP over R. And we're going to start at 1192. We're going to end at 298. And this is the Q from step 3 to step 4. And so that's minus 52,937 joules. All right, so the delta U for that step is going to be the sum of those two things. So 52,937 and the 7417. That's 52,937. So that gives me a total delta U of 45,520 joules. It was 45,520. Okay, oh, look at that. So minus 45,520 joules. And what I wrote here for the first integral, again, was a positive 45,000 joules. So the numbers are much larger, but the net change is still the same. All right? So that'll make sense. We're going to be doing a lot of stuff like this in the course. And the practical relevance of this hopefully it's starting to be clear already. So first of all, the amount of heat and the amount of work that it takes to change from one state to another very much depends on how you do it. The overall properties of the final state don't care. So the name of the game is to find the most efficient way to get from point A to point B. So if you're doing calculations, the most efficient way is the one that takes the least amount of effort. So even though a real process might take some weird curve through pressure volume space, you can achieve the same calculations by fixing one variable to be constant and only changing the variables that are the easiest to manipulate. Okay, so we're going to be doing a lot of that when we start to do like residual property calculations. So those are going to be discussed in chapters 5, I believe. It's where we take off the ideal gas approximation as it applies to changes in enthalpy and changes in entropy. So right now we're saying enthalpy for an ideal gas is only a function of temperature. Well, and that's really convenient to calculate, right? But that's not reality. So the way that we do it to make life easy for us is we imagine converting a real gas into an ideal gas. And so that's a state change, and the change in enthalpy associated with that is the residual property. But once you've converted conceptually your real gas into ideal gas, then you can use ideal gas laws to manipulate it. So you manipulate the ideal gas, and then once you're at your final state, then you calculate what the residual property is for that final state, and that makes it real again. Okay, so it's some mathematical hocus pocus, really, but it makes your lives easier. All right, another practical reality of the difference between path and state functions is in the real world. So if you want to calculate how much energy your internal combustion engine is able to produce, well, guess what? Is gas is in cylinders. And you're going from low pressures to high pressures and low volumes to high volumes. And the heat that is generated is not driving your car. It's waste heat. Right? So heat is generally the lowest quality form of energy that you can come across. The work is the valuable energy. That's what you pay the money for. So when you're designing an engine, you want a cycle that gets you the biggest amount of work per cycle possible and the least amount of heat required. So in this simple example here, this pathway took how much work? And it's written down right here, about 1.85 kilojoules. This pathway, the work was much larger, 7,400 joules. So it took 4 times more effort to do it this way than to do it that way. If you're a company that's in the business of compressing gases, you're probably not going to design a process that makes you do 4 times more work than you need to do. You're going to try to design a process that requires smaller amounts of work. That means smaller compressors. It means lower energy bills. It means less heat requirements. Okay, so there's real world reasons and paper world reasons for being able to manipulate those things. Okay, so the next thing we want to cover is we're going to pause on the whole state change topic for a minute here because we're kind of closing out chapter 2. And so you're mostly following the book here. So if you look at the outline on the left here, we've talked about internal energy. We've talked about first law. The first law turns into the energy balance for closed systems that you can use to do calculations. We haven't talked in class about reversible processes yet, but that's very important reading. We're assuming that all these processes are what we call reversible. And what that means is that these are ideal, perfect processes that don't lose any energy due to friction or other non-idealities. And again, the reason why we do that is because it's easier to calculate state changes if we assume reversibility. Now, when you go into the real world and there's a power plant that's got expanders and compressors, they're not reversible, but they do have efficiency factors associated with them. So again, what we do is we start with ideal calculations that don't represent reality, but they are easy to work with. And then you apply fudge factors basically to convert the idealized case in real world cases. And it's actually a system of doing things that works pretty well. So the last thing that we need to address right here is just kind of a reminder of mass and energy balances for open systems. And that's the last bit in the chapter. And you've done a lot of this in 210. So we're going to do a quick reminder of what the energy balance equation is. And if you look at chapter 2.9, it goes through a lot of different versions of it. And one thing I've noticed about Smith, Van Ness, and Abbott is it's very boxed equation happy. So it likes to box almost every equation like it's the most important thing in the world and you need to remember it. The only problem there is it's hard to determine what you really need to remember from what's just another boxed equation. So here is one of the ones that we use quite a bit. So it does become one that we need to remember. All right, so this is the open system energy balance. And we looked at one of these types of processes on the first day of class. Okay, so real quick, we'll walk through each term here. So the first thing you need to do with an open system is define what your control volume is. So if that's a pump, you're going to define your control volume to be the fluid in the pump. And you're going to look at the fluid going into the pump and the fluid going out of the pump. If it's a chemical reactor, your control volume is probably going to be the contents of the reactor. And you're going to be looking at streams going into the reactor and then streams going out of the reactor. All right, so this first term here is for systems where maybe a tank is being filled, and so the mass in the tank is changing at all times, or there's a chemical reaction that's not at its steady state, and there could be heating or something like that. Most of the time, or a lot of the times, we'll be looking at steady state processes, and this first term here will go away. So what this says is the rate of change of the intensive or the extensive internal energy in your control volume is represented here by this term. A lot of times it gets to cross that one off. All right, I don't know how my watch answered a phone call, and gotta love technology, right? Okay, so what this says is the rate of change of internal energy in the control volumes, the pump or the chemical reactor, plus the change in a bunch of energy terms going in and out of the reactor. So the subscript here, that means flow streams. And so this is a change in energy in and to and out of the reactor. All right, so the first delta in here is going to be the delta H. All right, remember delta H is delta U plus PV, and so the reason why for flow streams it's H instead of U is the stream that's going into the control volume is pushing and displacing fluid, and so it's doing work on the control volume, and so there is going to be a pressure volume term to calculate that amount of work, and then when the stream leaves the control volume is doing work on the stream as it pushes it out, and so there's going to be another pressure volume term that accounts for that. So rather than remember that pressure volume work all the time and continually have to add it in, it's just more convenient to define a new property that applies to certain types of situations, and that's the enthalpy. So when we do isobaric cooling, that's one situation where the enthalpy is more convenient to work with, and in open system energy balances, it's also the enthalpy that turns out to be more convenient to work with. Turns out you don't usually end up referencing the internal volume for a lot of calculations. All right, this 1/2 U here, that is going to be the mean velocity of the stream. So if you have a flow rate, you're going to divide the flow rate by the cross-sectional area, and that's going to give you the velocity, the mean velocity. So this, and so that's what the U is. So the mean velocity squared, so 1/2 mv squared, that's kinetic energy, right? This term is almost always neglected as well, unless there are really, really large changes in velocity or fairly heavy fluids. So for gases that are going from 1 meter per second to 20 meters per second, it sounds like a big velocity change, but if you actually calculate that in joules, it turns out to be not such a big number. So that's the kinetic energy. And it is usually negligible. Yeah. All right, this term, potential energy, and then everything, notice, is multiplied by m dot. So unlike the first examples that we've done where the specific properties that we referenced were like energy per mole, the most convenient form for the open balance, in its general form anyways, is energy per mass rather than per mole. And the primary reason for that is if you look at this, if it's n dot here, then number of moles times velocity squared does not give you a unit of energy that you need for your kinetic energy term. So you can use moles in here, but if either your potential energy or your kinetic energy terms you intend to keep, you've got to account for the fact that they need to be multiplied by the mass in order to correctly yield energy. Okay, and so this is all energy in minus energy out and energy accumulated, and that's got to be equal to the rate of heat and the rate of work that's being injected into the system. All right, so that is going to be good for today. So we'll traverse into chapter 3 then on Wednesday. And if you need homework help, a good time for that is 2 o'clock this afternoon. You can check Slack for those office hours. Also 11 o'clock on Tuesday. Or if none of those work for you, just use my Doodle Meet Me page to find a time when I'm available, and I'll try to meet with you one-on-one.
I think all of us are going to be at 3:57.
I have a question.
Yeah.
So when you were doing class, are you going to be close to the campus? I know I had a little trouble writing stuff down.